Hi guys, in this video we're going to look at functions, specifically relations and functions. They're not the same thing, but what we'll do is we'll sort that out later in the video. So sometimes the elements of one set are related to the elements of another set, and the example given here is consider the set x is equal to 2, 3, 4, 5, and the set y is equal to 4, 6, 7, 8. And the relation that we have here is a factor of from the set x to the set y. So this relationship can be written as a set of couples in the form xy, a bit like a coordinate, where x is a member of the x set here, and y is a member of the y set. For example, one couple in this relation is 2 is a factor of 6. And we call 2 the first component and 6 the second component of this couple. Thus we could write that our relationship, we can say 2 is a factor of 4, 2 is a factor of 6, 2 is a factor of 8, 3 is a factor of 6, 4 is a factor of 4, and 4 is a factor of 8. Notice that we can't use 5 here because 5 is not a factor of anything in set Y. Now for the language. So for this relationship, what we have is the domain is the set of the first components, i.e. the domain of R here, which is 2, 3, and 4. So 2, 3, and 4. The codomain of this relation is the set that the second components belong to, in this case y, which is 4, 6, 7, and 8. The range of the relation is the set of the second component. So what we're saying here is we've got 4, 6, 7, and 8. That there is the codomain. That's the possible answers for y. But we're only actually using, in our relation here, notice we're using 4, 6, and 8. We're not using 7, and 4, 6, and 8 is the range. So the codomain is all the possible answers we could get for y, whereas the range is the answers that we're actually using. In this case, 4, 6, and 8. We are not using 7, therefore it's not included in the range. So we can show all this in what's called a mapping diagram here. So we have our relation that we had from the previous slide, 2, 4, 2, 6, 2, 8. 3 is a factor of 6, 4 is a factor of 4, and 4 is a factor of 8. Notice that we have all of the inputs here. This is our domain. The inputs are the domain. And we have the codomain here, which is y. Okay. And we have the relationship here. As you can see that 2 is a factor of 4, 2 is a factor of 6, 2 is a factor of 8, etc., etc., etc. So let's have a look here at the domain. So the domain is all of the possible inputs. So the possible inputs are 2, 3, and 4. We aren't using the value of 5. The range is all of the values in the y that are being used. So we're using the 4, the 6, and the 8. So the range is 4, 6, and 8. Again, use your set notation. And the codomain is all of the possible values that we could have in the output or the y set. So we've got 4, 6, 7, and 8. We're not using all of them, as you can see here. So we're using only 4, 6, and 8. But for the codomain, that's all of the possible answers. So that's what we include. A function is different to a relation. It's a very special type. And a relation f from the set x to y is a function if each element of x is related to exactly one element of y. So here you can see that 1 maps onto 1, 2 maps onto 4, and 3 maps onto 9. So is this a function? Well, let's have a look at the definition. It says if each element of x is related to exactly one element of y. You can see this one here, there's the input, that goes to one output. This input goes to one output, and this input goes to one output. Therefore, this is a function. The fact that we're not using this 6 makes no difference. It says here it's a function if each element of x is related to exactly each element of y. 1 to 1 here, 2 to 4, and 3 to 9. So this is a function for exactly the reasons I've just given. Let's have a look at the second one. So you can see here we've got 2 maps onto 4 and 2 maps onto 6. So this can't be a function because the relation from set x to set y is a function if each element of x is related to exactly one element of y. And you can see here on this particular relation what we have is 2 to 4, 2 to 6. So the 2 is going to the 4 and it's also going to the 6. That makes it relation, but it doesn't make it a function. So we have to say no for this particular one. You can think about a function acting like a barcode for when you buy stuff in the shop. So if I was buying a Kit Kat and I scanned the barcode, I'd expect it only to give me one price, i.e. maybe a Kit Kat costs €1. I wouldn't then expect to scan a second Kit Kat and then it would give me €1.50. So it's a bit like a barcode function. You have one input, i.e. the Kit Kat, and it only gives you one output, i.e. €1. It doesn't give you two different prices. You may have seen this sort of idea of a function as a black box where what we do is we stick an input in, we do something to it. It might be, for example, add 3 and something comes out. So if I had 2, the function was add 3, my output would be 2 plus the 3, which would be 5, and we call that the output or the image. Now, we should also be aware of the f of x notation, which is here. This looks really complicated. And you can see here we have f, where what we do is we write the input, the output, maps onto the output, and then we give the function. Now, normally what you will have seen is something like this. Because we've always been used to dealing with just real numbers, you'll have seen f of x is equal to x squared, for example, plus 3. And then we stick numbers in to get our y values. Now think about it, we said a function gives a pair or a couple, an x coordinate and a y coordinate. All we're doing here is, because we've never actually used the whole idea of the input going to the output, we've just assumed there's always the real numbers, and therefore it just collapses down to this. So if you just see f of x or y is equal to, or f of x maps onto, and there's no input or output, which is what you've seen for the majority of the maths that you have done, then it just means for all the real inputs mapping onto all the real outputs, we get f of x is equal to whatever the function happens to be. Now here we are. We'll do a quick example down here where it says if f of x is equal to x squared, hopefully you can remember that what we do is we just sub in the values. So what we have here is we have 1 squared, which is obviously equal to 1. We have 2 squared for f of 2, which is equal to 4. And we have 3 squared, which is equal to 9. So if we go to one of these mapping diagrams, which we can see over here, then we can see that 1 is going to map onto the answer of this, which is 1. So we can draw 1 in here. We're going to have 4 for the second one, and the third answer we could have is 9. And we're going to draw that 1 maps onto 1, 2 maps onto 4, and 3 maps onto 9. And that there is our mapping diagram. So we have a nice little test that if we are given a part of a line here, for example, or a graph, we can check to see if this is a function by using what's called the vertical line test. Now what we do is we just draw a load of vertical lines here, as you can see here, and on the other one here we also have another vertical line. And to pass the vertical line test, what you have to do is you have to be able to draw a series of vertical lines, and what will happen is it will only cross through the graph once. So you can see here, it doesn't matter where I draw these lines as I go down or across the right here, it will only ever cross once, and therefore that means that this is a function, so we can write yes. Now if you look at the second one, when I draw the vertical line test, this fails on 2 levels. The first one is the fact that when I draw a line going down the vertical line here, notice how it goes through twice, goes through here and here. So that means this has failed the vertical line test, which means that this is not a function. Likewise, if I draw a line just outside here, can you see that this is not touching at all, it's not going through the graph at all. And that is another indication that this is not a function, it has failed the vertical line test. Okay, so let's have a look at some examples here. So we have a relation R is given by the following set of couples. R is equal to 1, 4, 2, 3, 3, 7, 4, 8, and 4, 9. Is this relation a function? And we have to give a reason. Okay, so let's have a look at this. So we have 1 maps onto 4, 2 maps onto 3, 3 maps onto 7, 4 maps onto 8, and 4 maps onto 9. Now remember the definition of what a function is. Functions is that every input has at most or only one output. So 1 has an output of 4, that's fine. 2 has an output of 3, that's fine. 3 has an output of 7. But here we have a problem. We have 4 has an output of 8 and 4 also has an output of 9. That means that 4 has 2 outputs. It's a bit like the Kit Kat. That means the Kit Kat here has a price of 8 and the Kit Kat has a price of 9. Makes no sense. Therefore, this is not a function. So, no, it is not a function because the input 4 has 2 outputs. Okay, so that's the reason why. For the second one, it says a function f, x maps onto y, has a domain of 3, 6, 7, 8, and a rule that f of x maps onto x squared minus 8x plus 3. List the elements that must belong to y. Well, if the x values are 3, 6, 7, and 8, that means that we should be able to get 4 answers using these values of x that will belong in our set y. So let's have a look. We've got our x. We'll do this as a mapping diagram, in fact. So we've got 3, 6, 7, and 8. The rule, I'll just draw a y, so there's our x, there's our y. Our function is that we've got x squared minus 8x plus 3. Okay, so first thing we're going to do is we're going to put f of 3 through. And if we put f of 3, we're going to get 3 squared minus 8 by 3 plus 3. Work that out, we get 9 minus 24 plus 3, and that's equal to minus 12. Okay, so that means we've got minus 12 there, so we can put that there, and we can put the arrow going across to show. The next thing we're going to do is going to put 6 through, so we've got f of 6, I'll do it up here, we've got f of 6, and that's equal to, and we have 6 squared minus 8 by 6 plus 3. If you whack that in your calculator, guys, you're going to end up with minus 9, so we can put that down there, minus 9, so that there is going to map on to minus 9. Put the next one through, function is 7, put 7 through, we get 7 squared minus 8 by 7 plus 3. And if you work that out, that's going to be equal to negative 4, so whack that in there. So 7 maps on to negative 4. And the last one is f of 8. So let's put that in, we're going to get 8 squared minus 8 by 8 and plus 3. And if you work that out, that turns out to be 3. If you put that in your calculator, it means that 8 mapped onto 3. And that means if we're going to list the elements, that means that our elements are going to be minus 12, minus 9, minus 4, and 3 must belong to the set of y. Okay, here's another one, example 2. So function g is given by g of x maps onto x squared minus 4x plus 3. Show that g of 2 minus x is equal to the g of 2 plus x for all values of r. Okay, so if we were just given a number, for example, if I was given g of 2, what I would do is I just put 2 through the function of here, which is x squared minus 4x plus 3, and I would get a value. So I'd get x, so 2 squared minus 4 by 2 plus 3. I'd work that out, whatever that happens to be. It's 4 minus 8 plus 3, and that's going to be equal to minus 1. So g of 2 is equal to minus 1 here. Instead of being given a number, I'm just being asked to put an algebraic expression through. So instead of putting 2 through here like I did before, I'm going to put 2 minus x. So let's just put that through. So g of 2 minus x. Wherever I see an x in my function here, I'm going to replace it with 2 minus x. And then I'm just going to multiply it out and see what happens. So that's equal to 2 minus x all squared minus 4 by 2 minus x plus 3. So just to show you again, we've got g of 2 minus x. We've got x squared, so that's 2 minus x squared, minus 4x, so minus 4 by the x, which is just 2 minus x, again, because that's what's in the bracket, plus the 3, and we're going to tidy this up now. So simplifying, what we have here is we have, this is a binomial brackets, remember, we just square the first one, square the second one, multiply them together, and then double. So 2 squared is 4. Then what we have then is multiply them together. So what we have is 2 minus times minus x is minus 2x. Double it to get minus 4x. And minus x all squared is plus x squared. Going to multiply out this bracket here. So we're going to get minus 4 times 2, which is minus 8. Then we're going to get minus 4 times minus x, which is plus 4x, and then we're going to get the plus 3 at the end. Okay, tidy it up a little bit. So we can look at the squares first. We've got the square here, which is x squared. I then have, looking at this, I have the minus 4x plus 4x, which is going to disappear. And then what I have then is the 4 minus 8 plus 3. So 4 plus 3 is 7. So 4 plus 3 is 7. Minus 8 gives me negative 1. I'm now going to do exactly the same, but instead of doing 2 minus x, I'm going to check it for 2 plus x. So let's put that through now. So g of 2 plus x. And wherever I see an x in this function, just like before, instead of replacing it with 2 minus x, I'm now going to replace it with 2 plus x. So it's going to look similar to this, apart from there's going to be 2 plus x in these brackets instead of 2 minus x. So g of 2 plus x is equal to 2 plus x all squared minus 4 lots of 2 plus x and plus 3, and we are going to multiply it out just as before. So if we do that, remember, square this one, multiply them together and double. So we now have 2 squared, which is 4. We're going to multiply these two together to get plus 2x this time. So 2x, double it makes 4x, so 4x, and then we've got the x squared at the end. Again, we're going to multiply this bracket, we get minus 4 times 2 and minus 4 times x. So that's going to be minus 8, and it's going to be minus 4x plus 3. Then we're going to collect everything together like we did before. So we've got x squared. Hopefully you can see again that this 4x is a positive. This is a negative 4x, they're going to disappear. So then we're just left with the numbers, and we have 4 plus 3 minus 8. 4 plus 3 is 7. 7 minus 8 is minus 1. And that means we can see that g of 2 of x, which gave us an answer of x squared minus 1, is equal to g of 2 plus x, which gives x squared minus 1. So these two functions are indeed equal. So we can show that g of 2 minus x is indeed equal to g of 2 plus x. Okay, and this is the third example. Now, it's important to notice here what this actually says. It says this is the complete curve of the graph that we have here. Okay. This means that this isn't continuing off to infinity in the positive x direction. It's not continuing to negative infinity in the x direction in this direction. So what we're saying is that this graph only exists between, look, minus 4 and 4, because it says it's the complete curve. So it says, taking the domain to be equal to r, explain why the curve does not represent the function. Well, if the domain is r, that means that we have to have an output for every x value, because domain, remember, is the input. If we don't have an output for every input, then it is not a function. Well, we are saying that we want every input, or the input, to be all of the real numbers, and all the real numbers essentially go from minus infinity to positive infinity. However, we are only seeing this graph because this is the complete curve. This graph only exists between minus 4 and 4, which means that we are not having an input of minus 5 or minus 6 or 5 or 6 or any of the numbers less than minus 4 essentially, or greater than 4. But we have already stated that our domain is to include, our inputs are to include all of the real values. This is not the case because we are only including the real values on this particular complete curve from minus 4 to 4. So therefore, it is not a function. Second thing it has to do is to state the largest domain that would let the curve represent a function. Okay, so the domain is all of the inputs. So what can we do here? Well, the inputs, the domain, where the x value is going from? Well, as we just stated before, the x values are going from minus 4 to 4. So we can state that the domain, okay, the x values have to be between minus 4 and 4. I've not written anything down for part I. I think you probably get it from the way I explained it, hopefully. Now it says, with this domain, state the range of the function. Well, the range is the possible values of y that it has here. And hopefully you can see that the possible values of y, let's have a look, the y is here, isn't it? Yeah. And the lowest it can be is 0 here. And the biggest it can be is 16. So it can have any value between 0 and 16. So therefore, the range for the domain that we have between -4 and 4, so between -4 and 4, the range, or the y values that it can take, is anywhere between 0 and 16. So we can write that y is between 16 and 0. And we're done.